So let's go ahead and get started here. We appreciate you guys joining our long coffee break on this Thursday, December 19th, before Christmas. So our next series is not going to start up till after January. So it'll be the first one in January, will be January 9th, but we'll go over that a little bit later. Today, we're going to be talking with Chris Desroches from Swegon. Chris is application and regional for Swegon. We're going to be discussing defrost control and condensate mitigation for Swegon for their heat pump chillers. So with that, I'm going to turn it over to Chris and let's get started.
Perfect. Thank you, John. So welcome. Thanks everyone for joining us today to talk about heat pumps. Weather's starting to get colder this time of year, so it's a little bit top of mind for all of us. I believe in May, there was one of the coffee breaks, we talked about the product introduction from Swegon for our Blue Box air-to-water heat pumps. So for today, we'll just talk about a quick recap for the product lines in case anyone missed the previous session. So we've launched in August this year, range of purpose-built heat pump units. So these are not modular units assembled at a factory. They're purpose-built depending on the size. So our smallest unit is 30 tons. Our largest size is 135 tons. We have 7 sizes within the range. And we have these available in 3 flavors. So we have our Tetris line, which comes as a cooling-only chiller. If we have cooling dominant loads in our building, we might want to mix and match that with some reversible heat pumps. Under the Tetris family, we also have our 2-pipe reversible heat pump. So we're going to use this seasonally to make hot water all winter, chilled water all summer. If we have the requirement for heating and cooling available year-round, you're going to look at using our Omicron 4-pipe multifunctional unit, which is a heat recovery heat pump that is able to produce hot water and chilled water independently, but simultaneously with a hot water and a chilled water set point. So we opted to call this a multifunctional unit because it's a key differentiator for this, whereas with modular heat pumps, if we have unbalanced loads in our building, we might not be optimizing the heat recovery. We could have some modules in heating and others in cooling. So that's one of the drawbacks with modular type products where we're not always guaranteeing that we're doing heat recovery. For us, with the way the product's designed on the refrigerant side, the coils on the machine are basically being used as condensers or evaporators if we're heating dominant or cooling dominant. So we're always performing that first level of heat recovery on the hydronic side of our hot water and chilled water system, and only rejecting excess BTUs from the building or absorbing additional heat when we're heating dominant. So all the machines will have 4 compressors. The larger the machine, the larger the compressors get, and 2 refrigerant circuits. So we often think of 2-circuit chillers or heat pumps as, we have good redundancy if an expansion valve's not working or a compressor, we still have the other half of the unit that can work. That is true, but really what the benefit is that we're going to dive into today is talking about defrosting and water temperature control in our building. And the fact that with a dual circuit heat pump, we're able to coordinate the defrost and have independent defrost. So while half of the unit is defrosting, the other half of the unit is still able to continue providing heating for our buildings. So just to recap, I don't believe we had the testing finalized when we did the previous presentation in May, but the operating testing has all been finalized and confirmed. So we're using liquid injected compressors as standard on our heat pump model. So this means we can generate 140 Fahrenheit water down to as cold as 14F ambient temperature. As our ambient temperature drops from 14, it's a little bit harder to extract heat from outside using the air, and we end up having a lower lift on the compressor essentially. So that will drop off, but we still generate 130 water at -4F. So it's really more closely related to typical condensing boiler temperatures that we're used to designing with for hydronic heating systems. And just to put it in perspective and compare the older generation of air source heat pumps that have been on the market, 3 years ago would typically not have injection scroll compressors. So this meant we saw a much more drastic drop off of our supply temperature output from the machine as it gets colder outside. So there were, those types of products we'd see being designed maybe to 14F with 113 water temperature. But with the liquid injection, because we're able to maintain the high lift, we're able to generate much higher water temperatures, and it's more suitable for use in cold climates where we still need high water temperatures at cold ambient conditions. So when it comes to defrosting, there's, it's quite a loaded topic, and you can reach out to your friends at Long. This is, a really condensed version of this to talk about. We could talk about defrost for an entire hour, lunch and learn. But really, when it comes to defrost, there's the water temperature stability we need to consider in our building and managing the condensate. So as you know, for any kind of heat pump, if we are cold outside, in order to extract heat, we have to send refrigerant to the coil. That's typically 20 F colder than whatever the air temperature is to get heat transfer from the air into the refrigerant circuit. So if our refrigerant temperature is below the dew point, we're going to get condensation from the air, and that's going to freeze and stick to the coil. So temporarily for 2 to 3 minutes, about once an hour or so, we're going to need to put the unit into a defrost cycle, which means even though it's a heat pump, we're temporarily putting it into cooling mode to melt the frost and ice off the coil. So buffer tank's going to come into play for this that we'll talk about in a few slides, but purely on the condensate level, this is an image of condensation happening as part of a defrost cycle. But the example in the math that we worked out in terms of figuring out how much water is generated, a 100-ton nominal heat pump will have between 90 and 100,000 CFM going across the coil. And it's really humidity that's driving the frost and ice buildup. So when we have really cold conditions and 99% RH at 17 F, we might still produce about 20 gallons of water every time that we defrost. But really the condition that will cause frosting the most is actually when it's warmer at a high humidity, because we can carry more moisture in the air at warmer temperatures. So at 39 Fahrenheit ambient with 90% RH, every hour when we defrost, we could be generating 42 gallons of water when that machine defrosts. So it's really important to have a plan and a strategy to be able to deal with that condensate. Feedback from a lot of architects and mechanical engineers is that roof membranes don't really like having ice. Water freezing and melting on the roof throughout the winter can cause damage to the membranes. And Blue Box, we have a lot of experience in cold climates. We're market leaders in Scandinavia and Northern Europe, so we have a lot of experience with cold climates and optimizing our defrost. So part of that is having dedicated logic on the machines. That was a requirement for the launch in North America to be able to do independent defrosting on these large machines to mitigate the effects of water temperature. But we also have a lot of tricks figured out with defrosting. So for example, we don't just shut the fans off during defrost. We actually modulate the speed of them according to the head pressure, because through our experience, we figured out that that's the most effective way to melt the ice and have short defrost cycles. We also have basically a way to tune the defrost according to the local conditions in the field through the parameters. So the concern with this is typically if it's warm outside, but it's very humid, if you're only defrosting on pressure, you could actually wait too long before starting a defrost cycle by allowing too much frost and ice to accumulate on the coils. Or on the other side, if it's very cold but dry, we could actually be going into defrost mode without actually having ice and frost on the coil. So the sliding defrost just allows us to basically tune it to your local conditions to find that balance between not defrosting too frequently and having acceptable efficiencies by not allowing too much frost to build up on the coils. In terms of managing that condensate after, we have coil heaters at the base of the coil, you can see up here. So if we have any water that hasn't made it to the drain tray, our drain trays are sloped, but we actually add electric heaters at the base of the coil. Small wattage, but just basically to ensure that we don't have ice building up here, because once you start building up ice on a heat pump, it's going to accumulate and get worse and worse. So we want to prevent that from building up in the first place. On the drain tray itself, we want to make sure that we have continuous drainage. So we have drain tray heaters going across the coils. And we actually provide these heaters with about 24 to 30 inches of additional cable length so that you can fit it through the drain outlet and fill it down the condensate drainage tubes. So now in the field for the contractor, as part of your designs, you need to put in a condensate collection header, collect the condensate and route that to a drain. So it's going to prevent a skating rink from basically building up directly below the units. And one of the other key features too is we've opted to go with a standard hydrophilic coating coil. So we typically see this on VRF type systems where you might have a blue coating. This is actually a coating that repels water, because after we finish a defrost cycle, if we have any water droplets left on the fins and we start the compressors again, we're going to freeze that immediately. And if that happens, we're going to start accumulating ice much quicker. And now we need to defrost prematurely than what we should need to if that ice wasn't forming there right after defrost. So in our labs,
Chris?
we had done testing. Yeah.
Hey, this is John. So with this coil coating, does that extend the defrost times from like say 60 above to longer numbers like 90, or what do you think?
Yeah, so like that's what I was getting at. In the lab, we had done testing where with standard fin tube, we defrost once an hour. With the hydrophilic coating, we defrost once every hour and a half. So
Okay.
we're spending much longer time in between subsequent cycles. So a lot of thought has gone into this. We're cold climate experts. We have a lot of experience doing large systems up to 20 megawatts for district heating systems with air source heat pumps. So it's nothing new to us. Where we also like to provide a lot of guidance is looking at our water temperature. And the example I always like to call out for this is, and this is really showing us the importance of having independent defrosting. If we look at a 100 nominal ton unit rated, we would actually find when we consider the individual outputs of both circuits. So keep in mind one circuit, when we rate this 100 ton unit at 95 F ambient, that's the capacity we have at 95 F. But for any air cooled chiller, because that's really what our unit is in this moment where it's defrosting, is it's acting as a chiller. As you decrease ambient temperature outside, our cooling capacity actually goes up. So if you compare the output at 95 F ambient versus 23, which is the moment we're defrosting, you'll find you actually get 20% more cooling capacity. So we often think with a dual circuit heat pump that we're canceling out. It's not providing any heating. It's not providing any cooling. That's in fact not true. It really depends on the conditions, because we also need to consider that as it gets colder outside, our heating capacity is decreasing as it gets colder. So at this condition of 23F, where one circuit's providing cooling and the other's providing heating, we actually end up being slightly cooling dominant, providing about 14 net tons of cooling capacity to our building. So when a typical heat pump we tried to design for 120 return, 130 supply, we're actually cooling it down by a couple degrees. So this is really important to factor into when you're doing water temperature calculations in your system. What happens if you have 4 units in a central plant? Even though we're only defrosting half the units at 23F, if we're still producing 14 net tons of cooling, what happens if you have 4 units defrosting at the same time? We could be cooling down our system by 56 net tons when we're actually trying to get heating out from our system. But what a lot of designers don't think about as well is we need to think of the heat load on the plant as well, because our air handling units or fan coil units, they don't care if the heat pumps are in defrost. They have valves that are opening asking for more water. So we need to consider that heat load as well, because if you undersize your volume too much with these heat pumps, you can, when you go and defrost, your supply temperature will drop off. You try to heat the water back up in the system over time, you're still pulling heat, so it takes longer to react. And then after an hour, we might have increased the temperature by 10 degrees and, oh, we got to defrost again, right? So it's kind of one step forward, 2 steps back. So this is why system water volume is going to be very, very important. So when we do a calculation for you, we don't just give you a basic rule of thumb. We'll look at this on a job by job basis. We'll look at the adjusted heating or cooling capacity that we want to get from the units at the condition that we're concerned about for defrosting, and we'll calculate it based on a certain stability for you. So we'd recommend a medium stability, which is sizing your volume such that in the worst case, when defrost is happening, we only see a temperature drop of 10 degrees Fahrenheit. So we'll look at this in depth with you, and there's a lot of sophisticated things. This is the last thing I want to wrap up with, but for central plant controls, Swagon's unique compared to other manufacturers with quite sophisticated controls. So we're coordinating the defrost among multiple units in a plant to prevent multiple circuits from defrosting at the same time. If you have units that are on standby, you will also, you can turn those on when another unit's defrosting to reduce the impact of water temperature stability. So we're very much about systems. So if you're interested, we could definitely set up a lunch and learn and tell you more about the different control solutions and features that we offer when it comes to heat pumps, and leverage the diversity a little bit. So with that, I think we're right up to the end of the time. Is there any, do you do questions on these, John?
Thanks again, Chris. No, I think that's perfect. I really appreciate you giving us a kind of a quick overview of how we manage defrost and how we manage condensate control. So, if there's any questions out there from the folks that are on the meeting, please reach out to your lawn professional and let them know if you have any questions. Chris, thanks again. And thank you everyone for joining us on our long coffee break. This is our 4th year we've been going into this. And we want to wish everyone a very Merry Christmas from all of us here at Long. So have a great day and a great holiday. Thank you.